Have you ever wondered how scientists knew where to place elements that hadn't even been discovered yet? Imagine designing a table with invisible tiles that somehow predict the future. That's what Mendeleev did. Back in the 19th century, Mendeleev arranged elements in a table based on increasing atomic weights. It was revolutionary, yet not perfect. Some elements, like argon and potassium, didn't fit the trend of increasing weight. Then came Henry Moseley, who, through experiments with X-ray spectra, discovered that the true order of elements should be based on atomic number, the number of protons or electrons in an atom. And that changed everything. The modern periodic law now states the physical and chemical properties of elements are periodic functions of their atomic numbers. So, rather than focusing on mass, we focus on charge, and that's what made the modern periodic table a powerful predictive tool for chemistry. Let's dive into how elements are arranged in this modern layout. The basis of classification today is the atomic number, and this aligns beautifully with an element's electronic configuration, that is, how electrons are distributed across its shells. This electronic arrangement determines both chemical reactivity and position in the periodic table. So, when two elements have similar outer shell configurations, they end up in the same group, which is a vertical column. The periodic table has 7 periods or horizontal rows and 18 groups in total. And within this layout, we see a beautiful organization of the universe's building blocks. Let's move across the table literally. Each horizontal row is called a period. What's fascinating is that a period always begins with an element having one electron in its outermost shell, like sodium, and ends with a noble gas like argon, which has a completely filled outer shell. Across a period, elements gradually shift from metallic to non-metallic behavior. For example, in period 3, we move from sodium, a reactive metal, to chlorine, a nonmetal that strongly attracts electrons. This shift is not random, it's a direct result of changing atomic structure, with electrons being added to the same shell and the nucleus pulling them in tighter. Now, let's look down the table at the vertical columns called groups. All elements in a group have the same number of electrons in their outermost shell, which explains why they have similar chemical properties. For example, group 1 elements, lithium, sodium, potassium, all have one valence electron and react vigorously with water. There are 18 groups in total. Groups 1 and 2 and groups 13 to 17 are called normal elements. These are your typical metals and nonmetals with predictable properties. Group 18 contains the noble gases like helium and neon, which are inert, meaning they don't react easily because their outer shells are full. Now that we understand the layout, let's highlight some special zones. Reactive metals such as sodium and calcium are found in groups 1 and 2. They readily lose electrons and form positive ions. In the middle of the table, you'll find the transition elements like iron, copper, and zinc. These are metals with variable valency. They often form colored compounds and act as industrial catalysts. In the upper right corner, we see nonmetals like nitrogen and oxygen, which tend to gain electrons and form negative ions. And finally, the far right group 18, the noble gases like helium and argon, are chemically stable because their valence shells are already complete. As we move across a period in the periodic table, certain properties like atomic size, ionization energy, and electronegativity change in a systematic way. Atomic size decreases from left to right because the increased nuclear charge pulls electrons closer to the nucleus. We also see a shift from metallic to non-metallic properties. Metals dominate the left side of the table while nonmetals dominate the right. For example, in period 2, lithium is metallic while fluorine is highly nonmetallic. Why do patterns keep repeating in the periodic table? It all comes down to periodicity, a repeating cycle of properties due to similar outer electronic configurations. Properties like valency, ionization energy, electronegativity, and metallic character show periodic trends. Let's break it down. After every 2, 8, 18, or 32 atomic numbers, similar electronic configurations repeat, leading to elements with similar chemical behavior. This is why lithium and sodium, although in different periods, show nearly identical reactions with water. And this is what makes the periodic table a powerful predictive tool, not just an organizational chart. Let's quickly revise what we've learned about the modern periodic table. We started with Mendeleev's idea of arranging elements by atomic weight, but Moseley's discovery of atomic number gave us the modern law that element properties are periodic functions of atomic number. We explored how elements are organized into periods and groups, each with their own trends and logic. We saw the classification of metals, nonmetals, transition elements, and the noble gases, and how electronic configurations dictate their placement. And we wrapped it up with the idea of periodicity, that beautiful repetition of chemical traits that makes the periodic table a map of the microscopic world. I hope this session helped you understand that the periodic table isn't just a chart, it's a story of electrons, patterns, and predictions. In the next topic, we'll explore periodic properties and their variations, like atomic size, ionization potential, and more. See you there.